The next few topics should be a little more familiar. It's not completely new. We're going to do some more applications of integration, but these are more applications in terms of applying integration to I guess to physical things, sort of. The first bit is not necessarily physical, but a little more something a little more familiar to us, I think, than differential equations and that kind of thing. So today I want to talk about arc length and surface area. We will come back to this. We'll come back to this idea in second semester, because in second semester in Calc 3 we'll develop some tools that will let us find our arc lengths and surface areas in a little bit different way, and we'll be able to find surface areas of more kinds of surfaces. All right, so I'm going to go through our a way of developing our equation for arc length. There are several ways, but I like this way because of what shows up. So what we're going to do is use the distance formula to develop our equation for arc length. So this is based on the distance formula. And this argument that we use to develop our equation, we will use similar arguments for a number of things over the next few days. And when we go a second semester in Calc 3, we'll apply the same kinds of arguments for three-dimensional things. So I hope that we'll become familiar with this kind of argument. All right, so here is some curve. So the curve is given by y equals f of x. And I'm going to call this p sub I minus 1. So this is point I minus 1. And I'm going to call this point p sub I. And I'm going to call the coordinates of this point x sub I minus 1. They were excited. And f of x sub I minus 1. So that's my x and my y. And this point would be x sub I, f of x sub I. And what we're going to do is approximate the arc length, the length along the curve, by the length of this secant segment. So our arc length between the 2 points p sub I minus 1 and p sub I is approximately I'm going to call it d sub I for the distance between those 2 points. D sub I is, using the distance formula, the square root of x sub I minus x sub I minus 1 squared plus my y coordinates, f of x sub I minus f of x sub I minus 1. I'm going to square that quantity. So that's our distance formula. And our arc length, S, is approximately the sum, if we break this up into a bunch of pieces, I equals 1 to n of the d sub i's. So we're just going to add up a bunch of these little secant segments and say that's approximately our arc length. All right, so this is why I like this argument, because we get to talk about the mean value theorem. So on this interval from x sub I to x sub I minus 1 to x sub I, what does the mean value theorem guarantee us? Mean value theorem says there's some points in there where what happens? The what?
The secant line is equal to the tangent line.
The slope of the secant line is equal to the slope of the tangent line. The mean value theorem guarantees us that on that interval, if we have a nice function, that there's some point. So I'm going to say this is why I like this, because we get to use the mean value theorem. By mean value theorem, there's a w sub I where the derivative at w sub I, the slope of the tangent line, equals the slope of the secant line. Well, the slope of the secant line is our change in our y values, x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. Or I can rearrange this. I'm going to say so f of x sub I minus f of x sub I minus 1 equals f prime of w sub I times x sub I minus x sub I minus 1. And now we're going to call this x sub I minus x sub I minus 1 delta x sub I. So I'm going to say let delta x sub I, change in the x value, equal x sub I minus x sub I minus 1. And what I'm going to do is substitute this quantity into my distance formula for f of x sub I minus f of x sub I minus 1. Because we have this delta x sub I here, and we end up with a delta x sub I there, and some nice things happen. So I'm going to say substitute. To get that our distance on that interval is the square root of delta x sub I squared plus this quantity f prime of w sub I times delta x sub I squared. Well, I can factor out this delta x sub I squared, and I get that this equals the square root, and hopefully this is a familiar quantity because I know you've seen it before, f prime of w sub I times delta x sub I. And we know that our arc length is the sum of these d sub i's, approximately the sum of those d sub i's over the interval. As we let delta x sub I approach 0, this approximation gets closer and closer, and we end up with the definition of we get a Riemann sum, we get the definition of an integral. So motivated by this, so I'm going to say as delta x sub I approaches 0, we get a better approximation. Oh, I forgot something here. Squared. Yes, Jim.
Go from the first square to the second one.
This one?
Yeah.
I factored out, so I have a delta x sub I squared here, and I have a delta x sub I squared here. Factor that out. So I have 1 plus f prime w sub I quantity times delta x sub I squared, and then I take the square root of that delta x sub I squared. So I combined a couple of steps there. So as delta x sub I approaches 0, we get a better approximation. So motivated by this, we define the arc length I had a professor in college that said, when you make something your definition, no one can touch you. So as long as your motivation, the math behind your definition makes sense, you make it, you say, this is how I'm going to define it, and then that's the end of the story. So motivated by this idea, we're going to define the arc length on an interval. The arc length S of f on some interval from A to B to be the arc length is the integral from A to B. I'm going to make this smaller. The square root of 1 plus f prime of x quantity squared dx. And that square root of 1 plus f prime squared, we call that our arc length increment, or arc length. We'll do more with that. You'll see that this quantity and similar quantities when we talk about surface area. We come up with a similar quantity. So there's our arc length integral. Now you might, yeah.
Do we need to know that whole process? We just didn't
No.
get there? Oh,
No.
okay.
But what I said before is we will make similar arguments for things in the future. So it's a good idea to not necessarily the details of one particular one, but just the idea to find a sum. We're going to divide things and make the subdivision smaller and smaller to get an integral. So we use that argument quite a bit. So we'll see that quite a few times. All right, so based on the way this looks, where we have an f prime squared and then we have a 1 plus something in the radical, what are we going to guess about these arc length integrals? They can be very messy. In a trig sub, you end up with lots of interesting integrals. So a lot of our examples tend to be the problems that we do tend to be a little bit contrived, because otherwise we have to you end up with integrals that are really tough to evaluate. And a lot of times you have to evaluate them numerically. But mainly we use this one because this quantity is so important. We'll see this quantity a lot in Calc 3. We'll talk about arc length. We'll spend quite a bit of time talking about arc length. We'll we'll talk about arc length and its relationship to curvature. So it's fairly important. All right, I want to do one quick example, and then we'll talk about surfaces of revolution. All right, so we good with our arc length formula? Okay, let's do a nice example. And this one is, it's a touch contrived, but it's nice. All right, so we have a cable. Between towers 200 feet apart. The cable takes the shape of a catenary. So if you assume that the cable is massless, then the shape of the hanging cable is parabolic. But if you assume that the cable has mass, the shape is not actually parabolic. It's what we call a catenary. And the formula is y equals 75 e to the x over 150 plus e to the minus x over 150. Does that look familiar? It's cosh. And because we don't have a 2 here, this equals 150 cosh x over 150. And if we draw a quick sketch, if these are my towers here, the cable looks something like this. And the equation here, it puts our coordinate system right in the middle. So this is y and this is x. And 0, 0 is right in the middle. And here in the middle, it would be 150 feet tall. And there's x equals negative 100, and here's x equals 100 at this tower. So that's the coordinate system that we're using here to get this equation. All right, we want to find the length of the cable. So you're out for a walk, and you see these towers, and you know from your GPS that they're 100 feet apart, and because of your knowledge of hyperbolic trig functions, you know that that's the formula for the shape of the cable, and you say, I wonder how long that cable is. All right, well, we're going to use an arc length formula. You could do this problem using the exponential functions. And the book goes through an example using this same kind of problem using the exponential functions. But we're going to do it this way. All right, so y prime, since we've been working with hyperbolic trig functions, we need to find y prime to find our arc length. So what's y prime here? Isn't it sinh of x over 150? So we get the 150s canceling out. Y prime squared is sinh squared. And hyperbolic trig functions are a lot like regular trig functions. When you see a sinh squared, that's a good thing often. 1 plus y prime squared for our arc length radical. 1 plus sinh squared x over 150, which is what? Cos squared. Oh, this is great. So our arc length is the integral of the square root of this. So that's just going to be the integral from negative 100 to 100 of cos of x over 150 dx. Nice, easy integral. Yeah? Oh, no, because we take the square root, right? The arc length is the square root of 1 plus f prime squared. So the squares go away. So it makes it even nicer. And when we integrate this, we get 150 sinh x over 150. And we're going to evaluate that at from minus 100 to 100. And now we go back to to evaluate this. If your calculator doesn't have hyperbolic functions, you can go back to your definition of the hyperbolic sign. And when you do that, you get that this is approximately 215 feet. You have to have 15 extra feet in that cable for the sag of the cable between those two towers. Isn't that nice?
So nice.
Yeah. So often your examples with arc length integrals are going to be like this, but there are some nice integrals that you end up having to evaluate. Yes?
So we would get a calculator for this type of problem if we had to evaluate.
Yeah. Yeah. Yeah, I don't. E to the 100, that would be a tough one to do in your head. But well, of course, when you're out for a walk and you have your GPS, you probably have your calculator also. You probably have your calculator apps on your phones, right? That you can do the hyperbolic trig. Yeah. I have at least 5 calculator emulators on my phone. At least 5.
Do you do this like when you're on the walk and you see a cable?
Oh yeah, I better measure that too.
Yeah. All right. Last thing for today. But all of my emulators are HP calculators. So on your handout, I gave you a handout, and I kind of circled and I highlighted along one edge. It says areas of surfaces of revolution. And what that does is, for a surface of revolution, what we're going to assume is that the small piece of a curve, we revolve that around some axis, and this surface that we get when we revolve this around an axis, we're assuming is a small, if we make this change the distance along the curve small enough, we're assuming that that portion, that surface, is a portion of a frustum of a cone.
Can you say all of that again? I lost you.
So we're saying if we're revolving this curve about an axis, like so, we say that surface that's generated, if this distance is small enough, that surface is approximately a piece of a cone with the top cut off. So we're going to use the area of the frustum of a cone as our surface area for our surface area integral. And it goes through the derivation on that worksheet, how we come up with a formula for the area of a frustum of a cone. So that's the formula that we're using in our arc length integrals. So the area of a frustum of a cone is frustrum, isn't it? I believe. Frustrum? Frustum? Okay. Frustum. I had a student a few years ago that thought that was the funniest word in the world. Frustum. Area of a frustum is 2 pi r bar L, where this is the average radius. And this is the slant height. So slant height means the height along the side of the cone. So the area of that frustum is 2 pi r bar L. And if we make the distance, that delta x, small enough, the r bar is essentially the radius of revolution, and the slant height is the arc length along the cone. So the slant height, the distance, is this arc length along here. So that's where integral comes from. So we're going to say our area of a surface of revolution. And we use a big S for area of a surface of revolution. S is the integral from A to B. We get a 2 pi, that's from this, and then our radius of revolution, r sub x, and then L, the slant height, is the arc length along that curve. So this is the r sub x is the distance between the graph and axis of revolution. And this is for y equals f of x. If we have x is a function of y, g of y, we get that our arc length, or our surface area of revolution, is the integral from a to b of r sub 2 pi r sub y square root of 1 plus f prime of y squared dy. Oh, this should be a g. Thank you. And r sub y, again, is the distance from the graph. This is the radius of revolution. So you'd use this top one, usually use this top one if you're revolving about the x-axis. And you'd use this one for a revolution about the y-axis. So this 2 pi r arc length comes from this 2 pi r bar L that it talks about in the handout that I gave you. That's the area of a frustum, of a cone. And we make the delta x's smaller and smaller and smaller, and we end up with an integral just like our last arc. All right. Again, the examples that we do with these where you can actually evaluate the integrals tend to be rather contrived. But let's look at a quick example of applying this. We want the area of the surface generated by revolving y equals 2 square root x about the x-axis. From x equals 4 to x equals 8. All right, so if I draw a quick graph, we get something that looks like this. All right, so there's y. We need y prime is x to the minus 1/2 when I take the derivative of that. What's our radius of revolution? Well, it's going to vary, right?
Yeah.
So what's the radius? It's going to go from here to here? 2 square root x. That's our function value, right? Our radius is going to be whatever the function value is at that particular point. R sub x is going to be 2 square root x. Our radius varies as we go from 4 to 8. And the function tells us how our radius varies. So the distance from the axis of revolution to the point is our y value. So our arc length is going to be 2 pi integral from 4 to 8 of our radius, 2 square root x, times our slant height, which is the arc length along there, 1 plus f prime squared, x to the minus 1/2 squared dx. This is nice because I get to show you this or remind you of this little trick. I'm going to write this as 4 pi square root of x, square root of 1 plus 1 over x, x to the minus 1. Now you might look at this and say, "Oh, we can't integrate that. That's really ugly."
We're done.
Yes, please.
But let's do this.
Oh.
Let's simplify that radical. Sorry, 4 pi. I'm going a little trying to go too fast. Square root of x. Let's find a common denominator. Square root of x plus 1 over x dx. Well, I have a square root of x here and a square root of x there. What happens? They go away. And now we have an easy integral. This is just a power rule. Was this our integral of the day? No?
It should be our integral.
4 pi, this should be the integral of the day. Yeah. Times, what do we get? 2/3 x plus 1 to the 3/2, evaluated on 4 to 8. And I'll write the answer out nicely. There's our exact answer. I didn't put this in decimal form. All right, so that's the kind of thing that you'll see on these kinds of integrals. There's some little algebraic tricks that you can do so you can actually evaluate them. I hope you're not talking about me, Lily.
No, I was saying how that's how it feels a lot. This time, I actually understand kind of what you're saying.
Ah.